This is not anywhere in your booklet. Just tell me if this is true or not. True or not? How do you read this out loud? 6 is greater than 5. True? Ooh, talk to me about that. What do you mean that? What do you mean that could? We don't know what x is, do we? I have to assign a value for x in order for you to evaluate that to tell me whether it's true or not, right? What if I told you x is 6? If I tell you x is 7, 8, 3, 2, 0, negative 9, 1.6, 8.6. Okay, so we could say that this is true for all statements, or all values that I assign to x, that are greater than 5. What about if I tell you x is 5? It would be a false statement because it has to be greater than 5. What if I tell you that x is 5.00000001? What if I tell you that x is equal to 4.99999 to infinity? Okay, so you get the idea. Okay? How do you read that symbol? Greater than. How do you read this symbol? Less than, right? Tell me if you know this one because this might be new. Raise your hand if you've never seen that before. Raise your hand if you have seen it before but you forgot what it is. Raise your hand if you've seen it before and you know what it is. How would you read it out loud? It's a good guess, but no. I'll give you, let's see if you can figure it out. We'll do this backwards. True or false for 6? X is 6. Okay, it's true. 7, 8, 9, 10. And now I'm going to tell you it's also true for 5. Correct. And you see a little line underneath it. You read this as greater than or equal to. So that now means that's now going to include all values for x, including 5. And then we go 5, 6, 7, 8. And it doesn't have to be just integers. It could be rational numbers, 5.1, 5.2. But it also now includes the integer 5. So it can be equal to or greater than. Okay? Here, up here, no. It has to be, this means it has to be greater than 5. So it would not be true for 5 if x was 5. So you read this as, everybody say, greater than or equal to. Say it out loud. Therefore, this is going to mean what?
Less than or equal to.
You got it. So now, that being said, let's take a look at page 2. Everything that I just summarized with you is in this little graphic chart for you. Okay, so if you need to refer to it and you forget, that's okay. Use, go back to it and take a look. Okay. Here's what I want you to do. I want you to solve y plus 6 equals 16 using railroad tracks. Do that right now. Step back so everybody can take a look. You do everything perfectly? If it was a quiz, would it be full credit? And now, you know what? Do me a favor, though. Circle y equals 10 for me. So let me ask you this, guys. Raise your hand. What's the only value that y can be that makes that statement true? Carson. 10 and 10 only. Anybody want to come up and do letter B? Okay, so now, what do? I want you to treat this exactly like you would treat any railroad tracks equation. Even though it doesn't look like railroad tracks anymore in the middle because you have an inequality in the middle, but still solve it the same exact way. Go ahead, Jen. This is good. This is becoming routine for you, which is going to give you quite of an advantage when you get into 7th grade because you'll be doing a lot of this. How many of you see have done it the way that Jen did it? Okay, it's all good. Make believe they're equal signs, but here's where it's different. When you read this now, you need all values for y that are greater than 10. So what's the very first? Let's stay with integers because we can assume that there are some rational numbers in between. But if you stick with integers, what makes this statement true? Starting with what number?
11.
Right, 11. Exactly. It goes on for forever, and then you do like everybody know that that's the infinity symbol? Okay, it goes on, and just keep in mind, even though I'm writing only integers, it's going to be true also for all of the rational numbers in between. Finally, come up and do letter C. Someone. You'll see it's almost exactly like the first two. Everybody got that? What's the only difference between part C and part B when you list your set? Yes.
In part B, in part C, it could be either 10 or greater, and part B.
Right. So now in letter C, we can now include 10. And then it pretty much matches up with everything that we did in part B. Because it could be greater than or equal to for it to be true. So we could start with 10. Anybody want to come up and solve 3g equals 15 using railroad tracks? Nate, you have to reach a little bit because you can't scroll any lower.
Try it.
Oh, you'll be fine. Circle it. You're good, bud. Everybody got g equals 5? Stay up there. What's the only value that will make that statement true? Bud, what's the only value that g can be to make the statement true?
5.
Correct. So where it says true, put 5 and 5 only. Okay, we're good. Let's come up and do A.
Alice.
It's been corrected on your sheet. You're right, though. Who wants to do B? Eleanor. Mm-hmm. Looks good. All right, wait. What's the only value or values that's going to make that statement true? And just let's assume integers. Don't worry about the rational numbers. Okay, so start listing. Do a 4, a 3, a 2. And then you can do the little infinity symbol. I bet you could probably do the infinity symbol better than I did. I can't do it. I have to turn my whole head on the side in order to do it. See, look how perfect that is. He's got it. Very good. I know, but I can't. I have. I know I'm strange when it comes to that. I don't know. She's just good. Okay, he wants to come up and do C.
Drawing is drawing.
That's it. You got good spatial relations. All right, finish it up now. I just had put it on pause just to save time, so on the blob. Can it now equal 5? Right, and everything below. Right? Everybody see? That is read as G can be less than or equal to 5. Very good. Okay, next example. Building on what we did in the previous examples, solve for n. Right now, solve for n like you would normally do. All right, how do you read that out loud?
N greater than 13.
Okay, n is greater than 13. Can it be equal to 13? Can it be equal to 13? Okay, so now the way this differs from the examples is they give you the rational numbers, and you have to tell me whether it's true or not if we substitute that in for n. If n is 15, is the statement true? Yep, because 15 is greater than 13. I'm writing yes. If you want to put true, you can. What about if n is 8? Okay, that would be an affirmative no. 13 and a half. Oh, absolutely. Negative 25. Anybody want to come up and do number 2? Come on, you want to try it? Did everybody get x greater than, or y is? If you notice, he flipped his inequality by accident. So let me just repair this. See that kind? It's got to go this way. Y is less than or equal to 10. Okay, let's evaluate the statements. Will this work if y is 5? What about if y is 15? What about if y is 10? Yes, because it can be equal to -9. Okay? Try this one all by yourself. I'll come around and check. Number 3. What you're going to start seeing me do more of, because I want you to get used to it. I know I introduced it when I was doing railroad tracks, but here it is again. When I want to multiply, I'm going to put in parentheses rather than using the dot. So I don't want dots to get confused for decimals. These cancel out. Y is now less than 24. It's got to be less than, but it cannot be equal to. So it's yes for 0. 23 9/10. It's smaller by 1/10, but yes, it's good. Yes, yes, no, no. Most everybody got to hang up. What do I have to do to both sides? All right. Correct. X can be greater than or equal to 15. Can it equal 15? So you got to put yes for that. Negative 15 is definitely a no. So is 0. But 30 is a yes. Any questions on that? Okay, last one. Do what to both sides? What cancels? What's 42 divided by 7? All right, here we go. Is 6 less, 6 and 24, 58, is that less than 6? Is negative 6 less than 6? Is 6 less than 6? Right, because it can't equal it. Is 7 less than 6? Is 7 and 1/785 less than 6? 7.000009. 6.999999915. Negative 7.9999. How many got 100? Are you good now?